In fact, some of them are already exercises in the book. So there's that. So as I said, I mean one of the main reasons why we have to be careful when studying convergence in series is the fact that there's this kind of pathological things where you have that the sequence, there are certain sequences, you take the absolute values of the terms and you add them, they do not, I mean the corresponding series does not converge, but you can add them in different ways. I mean, changing the signs or whatnot. Even if you fix a sign to each a sub n, like here in the case of alternating series, and you may end up with completely different values. I mean, you may end up with convergent series, but converge to completely different values depending on the rearrangement. Okay, so now the next thing is to go back to rearrangement, which is something we've already discussed plenty of. But before moving on, let's try to introduce some notation. So we're going to say that so this is just a convention. So we say that the sum n equals 1 to infinity converges absolutely if sum from n equals 1 to infinity of the absolute value of an is convergent. If this sum does not converge, but the sum of the ANs does, then we say that the series a sub n equals 1 to infinity converges only conditionally. So for instance, again, the typical example, the alternating series minus 1 to the n plus 1 divided by n. So if you add all these things, I mean, this converges conditionally. And here order matters. So this converges conditionally because the sum of 1 over n does not converge. So because remember that the sum, I mean, this series converges by the alternating series test, while the sum of the of 1 over n does not. Is divergent. Right, and there are other series that converge. I mean, the geometric series, like the sum of 1 over 3 to the n minus 1, the sum of the minus 1 to the n plus 1 or 2 to the n also converges absolutely, just like the sum of 1 over 2 to the n, because they both have the same associated series of absolute values. And so this is important to keep in mind. There's a very big difference between conditional convergence and absolute convergence. In fact, absolute convergence in itself prevents some of the pathological things we've seen regarding rearrangements. And in fact, we have a theorem about it. 2.7.10 says that if a series converges absolutely, then any rearrangement of the series converges and does so to the same limit. Again, and to the same limit is actually kind of the point. I mean, we already seen that you can rearrange, say, the alternating series of minus 1 to the n plus 1 over n to obtain basically any value you want. So we can make it converge. I mean, this is not. I mean, you can also make it diverge choosing the right rearrangement, but yeah. So but the point here is that no matter how you shuffle the terms, you're going to obtain not only a convergent series, but you don't have a choice on what this new series will converge to. So no matter how you start adding, how you add the terms, you're going to obtain the same value in the limit. And this is the important point. So what is the proof? So I'm going to sketch this for you, but let's start by noticing what we have. So we have that we know that okay, we should probably introduce, we're going to use let's just immediately introduce a series, so then the rest is implied. Just the series, it's the series of the ANs equals 1. To infinity, be an absolutely convergent series. Since it's absolutely convergent, we know that the series, when we made of the adding the terms, the absolute values of the ANs converges as well. So we know that converges. This is just the definition of absolute convergence for the series AN. So suppose we have a rearrangement. We suppose a sub phi of n is again, in case you forgot, a rearrangement is a bijective function from n to n. So we're just shuffling the terms, so we have the same terms, and we are not counting any term twice. I mean, every term here will appear here, just in a different order, and it will appear only once. So it's a bijection. So phi is a function from n to n, which is a bijection. So we have a rearrangement of the original sequence. And what we do know is then that suppose that we have, okay, so n equals 1, 2, up to a certain n. It's just a sub phi of 1 plus a sub phi of 2 up to a sub phi of capital N. Okay, and this is Sn, right? So what we want to show is that Sn converges to the limit to the sum of the ANs from n equals 1 to infinity. We want to show, and that means we want to show that the Sns are a Cauchy sequence. That Alright, so how do we do that? Well, let's notice something. So let's start by giving us some number epsilon greater than 0. So let epsilon be greater than 0. Now we know there is n, or let's use m, capital M now, because we're using capital N for the rearrangement, such that for all n greater than m, greater than or equal to m, the sum of a sub n, but in absolute value, so the a sub k, I'm sorry, sum of the a sub k's is less than epsilon, because the series is absolutely convergent, so that means that the series of the absolute values of the AKs converges, meaning that the partial sums, or the partial sums, the sequence of the partial sums is a Cauchy sequence, and this is the Cauchy criterion applied to the partial sums. So we know this. So what is the idea now? So suppose the sum of the AKs, so k equals 1. Where is some number L? Right? We know. I mean, that we know that the sum here converges to some. This series converges. It's absolutely convergent. So the sum of the AKs, so the partial sum of the AKs, converges to some number L. So what we want to show is that S, the partial sum corresponding to the arrangements, is small, provided n is big enough. So we want this to be less than epsilon for n big enough. This is what we want. This is what we want to show. And how do we do this? Well, let's notice that, as I said, we're going to take advantage of the Cauchy criterion for this for the series of the absolute values of the AKs. Right? So that means that Sn here since we know that Sn is the sum of some of these terms, in the original sequence, we're going to choose n. So since phi is a bijection, for some value of n large enough, phi 1 to phi n, so this set will contain 1 up to m. So you have all the sub indices. So this is we're going to call, so we'll call the set A, and this is going to be the set B. So somewhere in the sum, you're going to have A1, you're going to have A2, A3, etc. up to AM. And now, because of this property here, we know that the sum of the a sub phi k's such that phi k does not belong to B, and this an absolute value, is going to be very small, because this is going to be part of the tail of the series. This is going to be a sum of this form. It's going to contain subscripts that are greater than or equal to n plus 1. And it doesn't matter how big n is, this inequality is still going to hold. So no matter how many terms in here you're adding up and how big n is, this sum is guaranteed to be smaller than epsilon. Therefore, what we have is that then that Sn minus L is less than or equal to the epsilon. It's actually less than epsilon, plus the sum of the phi k's not in B of the absolute values of the A of phi k's. And this is also smaller than epsilon, so we get this is smaller than 2 epsilon, provided n is big enough. So what do we want here? So we want to choose m at the beginning, so that we know that the tail here is really small of these terms. And we also want to choose n now, which will depend on m, so that the set A contains all the this set contains all the first m terms of the sequence, and what's left is going to be something that's going to be smaller than epsilon because of absolute convergence. Right, so no matter how we add the terms, then we're going to obtain the same limit L. And this concludes the proof. I mean, of course, you prove that this was smaller than 2 epsilon. So if we choose epsilon over 2 here from the beginning, no, I'm sorry, not epsilon. We choose an m that will guarantee that this is less than epsilon over 2, and that this is this here is less than epsilon over 2 as well. This epsilon here comes from just adding the terms a sub k from k equals 1 to m minus L. And since this converges to L, this thing converges to L, then if m is big enough, you perhaps need to make m a little bit bigger, but this will be less than epsilon, provided that m is big enough. And what's outside is going to be less than epsilon for sure. This is because of the absolute convergence of the series of the A sub case. Okay, so now you're just going to be given some exercises, and the next thing we're going to be doing is to go over some topology, some basic topology that we all need to know to present some of the theorems in the next chapters in corresponding sections and subsections. Okay, this is it for now, and we'll see you in the next video. Good luck. I mean, if you have any questions, again, just feel free to make an appointment or an appointment for Zoom, or to drop by for office hours.